All right, we'll start with the video. Okay, why don't we go ahead and get started. So welcome back, everybody, to EE240. So this is obviously the last week of classes. I know technically we're on RRR or whatever the acronym stands for, but we've got a couple things that I wanted to finish up, and then obviously the main thing is I want to actually give you guys a chance to ask some more questions on the project. So with that, I guess I'll do the quick poll. Who's now at least started on the project? Okay, good. So now, who's got questions on the project? It should again be everybody. Okay, Eric?
If we're using the default comparator, is there a minimum output swing?
Okay. So I don't think I actually specified it in the project handout, but don't be unreasonable, right? So if you're receiving a couple of millivolts at the input of your comparator and your output's only going a couple of millivolts, then that's no good. So let me maybe specify it this way. So basically, your outputs have to essentially be quote-unquote stable by the time you clock them. In other words, if there's, and let's maybe even make it a relative spec. So let's maybe even say that if your output swing is, let's say it should be at least 200 millivolts at the output of the comparator, which I think is about what I gave you, right, approximately speaking. So let's say that that one has to settle to within, I don't know, let's say 2 millivolts in order for me to call it a good digital level. Probably a little bit too mean, but just to make sure that nobody tries to abuse anything. Does that make sense? Or?
In like 1% final value.
Exactly. So if you're using like a 1 volt swing, that would mean like within 10 millivolts. If you're using a 200 millivolt swing, which is probably what I gave for the default at the output of that CML comparator, 2 millivolts is what you need to settle to within. Other questions on the project? I'll start picking on people if I need to. So.
What was the lowest power consumption last year?
What was the lowest power consumption last year? That's a good question. I think it was in the ballpark of 2.5, 3 milliwatts, something like that. Now, by the way, remember, you don't necessarily have to be going for the absolute lowest possible power. The point is you really need to be sitting somewhere on, if I have my power versus bitrate curve, you should be sitting somewhere on the line, right? So I think this number over here, which was at about 3 gigabits per second, which I said was the minimum, I think that was around 2 or 3 milliwatts, somewhere in that ballpark. By the way, just so that you know, people in real life have built links that operate at about 1 milliwatt per gigabit per second. And that's like the entire link, including all the clocking and things like that we haven't really talked about, which we'll actually talk a little bit about next lecture. But so that's, if you're hitting in that ballpark, that's a pretty reasonable ballpark. In fact, because we're not doing things across process corners and things like that, you can probably even get a little bit better than that. More questions on the project? Must be more questions. Don't make me start picking on you guys.
If our swing only used to be 200 millivolts, then get away without the comparator.
Not quite. So this needs to be a digital level, though, right? So in other words, I need to actually reject noise. So I guess what I'm getting at is that, so maybe you're saying something like, okay, yeah, I could just build my transmitter and blast this thing so hard that I have, I don't know, a volt of swing over here, that I still get, I don't know, maybe even 100 millivolts of swing over there, something like that. But I want actually like full digital levels. In other words, if I look at the eye diagram of your output, I want it to look basically like that. Right, so the output of your comparator better have a nice clean eye diagram. If the output of your quote-unquote link looks like, obviously my drawing's not great, but like that, then that's no good. Okay? So no cheating, in other words, because you have to actually receive the bit. It needs to be a digital link. That means you have to make a decision about whether it was a 1 or a 0. Other questions? Okay, I guess I'm going to have to pick on somebody. Jaehua, any questions? No? I told you if you didn't have any questions, I'm going to dock you guys. So now I'm going to have to like go one by one. Juan, any questions?
Yeah, I did have a question.
Okay, good.
The 1 milliwatt per gigabit per second, that was for the whole link, transmitter included?
That's transmitter, receiver, phase lock loop, clocking. That's basically everything.
Everything.
Yeah, everything.
For the offsets, you wanted us to compute the offsets for everything, right? So that's including like the transmitter if we change it.
That's right. So basically everything that has a MOSFET associated with it has an offset in it. So even though I gave you, for example, like the CML comparator and the transmitter and things like that, you have to include all the offsets inside of those blocks as well. Yeah. So even though I gave you those things, sorry, they have offset too. They're real circuits. Eric, did you have another question? Or? When you say different width, you just mean effectively different multipliers?
Yeah.
Oh, well, so that's a good question. So if you have something like this, and let's say this is a 1x and this is an mx, right? So you can always think of this as sort of conceptually, it's as if I've really got one transistor over here, and there's another transistor over there, right? So let's say that these were both effectively 1x. So that you certainly know how to do, right? That's just, essentially we said that the offset between them was using that AVT that I had given you, right? Okay, so let's pretend that I somehow wanted to match this to some, let's say, non-existent but other transistor that has no variation. If I looked at the mismatch between that one and this other non-existent perfect transistor that has no variation at all, how would I sort of change the AVTH parameter to account for the fact that that other transistor has no variation in it at all?
Divided by 2.
Ah, okay, so is it divide by 2?
Root 2.
Yeah, there we go. It's square root of 2, right? Because that other, right, I'm taking essentially something like VTH of transistor 1 and comparing it to VTH of transistor 2. Each of these has some random variation with a certain sigma associated with it, right? So remember, you have to do root sum squares because unfortunately subtraction is the same thing as addition in terms of random numbers, in terms of variances. So effectively, you just have an AVTH that's square root of 2 smaller than that, right? So now if you know this, I claim you should know how to answer that first question. Okay, because you can kind of individually take those AVTHs and then do the root sum squares. You'll figure out, or rather I should say, not the AVTHs, but the sigma of the VTHs, you should be able to figure out what that mismatch ends up being. Does that make sense? Or in other words, you can compare both of these to the magic transistor that has no mismatch, subtract their sigmas, and then just, again, be careful that when you do the subtraction, that actually adds the root sum squares. Okay? More questions? Or? Okay, so now we have a little bit more people. So everyone has started? Raise your hand. Okay, well, so you've got like less than a week now, and as I've warned you multiple times, it's going to take you quite some time. So, if you're not well into it by now, then definitely get your butt moving. We've got somebody here who took it last year. They'll confirm that it will indeed take some time. So, trust me, just go ahead and get going on that. So, unless there's any other questions, just one other sort of administrative thing. Attendance on Thursday is going to be required just because I want to make sure everybody comes in and gives their feedback for Eta Kappa Nu. So, sorry, I know it's the RR week, but you got to be here because I want you to fill out the forms, and then I want to actually just make sure we've got everybody here to have some discussions and things like that on any last issues of the project. So, last time we were basically talking about sample and holds, and really how we would build those and kind of what all the issues are with really how you'd build those switches. So before we dive back in, are there any kind of questions hanging on from last time? Or? Okay, so where we basically ended up was we had talked a bit about sort of what happens with the resistance of the switch, and in particular, why it's a little bit annoying to get sufficiently low resistance, particularly when the input is right around VDD over 2. So we talked about using transmission gates and things like that. And then we moved on to talk a little bit about, okay, when the switch is actually off, what we really want to make sure is that the switch is essentially completely open circuit, right? But of course, even though it's off, there's always going to be some small amount of leakage current flowing through that transistor, just due to the subthreshold leakage. And in fact, not only that, there might even just be a little bit of stray capacitance directly from the input to the output. So as it turns out, if you really, really have some very high precision applications, that even that tiny little capacitance or the tiny little bit of leakage could be a problem. Because you can imagine, let's say that, let me draw V in with some red waveform here. Let's say that that thing is doing something like this, okay? And let's say that I wanted to sample V in just right there, okay? So if I looked at, let's say, V out, it would track, and then in theory it should stop and just track perfectly like this, right? It should just sample it perfectly like that. Well, unfortunately, what's actually going to happen is that because of that stray capacitance, you're still going to actually move around along with the input, right? Now, I've obviously exaggerated it quite a bit here because I'm tracking almost perfectly with the input there. But basically, just that capacitive divider means that I'm going to feed directly through, right? So my output's still going to wiggle around even though I've tried to turn the switch actually to be off, okay? So last time I'd sort of left this to you as almost as a little bit of a homework exercise. Is there anything I can do to try and actually reduce this coupling from a design standpoint? Is there some way I can sort of make it so that I really do just sample the output and kind of leave it there or have it as isolated from the input as possible? Are there any tricks I can play? What do you guys think?
Cascode.
Actually, that's not as bad of an idea as you may think. Now, the only minor problem is I can't actually cascode things that don't have, like, current constantly flowing through them. But that's actually not such a bad idea.
Something like a cascode.
Okay, something like a cascode. I definitely agree with that. So if I was just doing the sort of zero-order cascode, that would say something like, okay, I've got my switch transistor over here, right? Now, and let's call that, let's say, V in, and let's say V out. Right? Okay, now, if I've added this thing to sort of be a cascode, if I really want to isolate this output from this input, I probably don't want to leave this cascode transistor on, right? Because that just means it's going to feed right through. So let's actually go ahead and tie the gates of these two things together, okay? So this is like my control signal now. Okay, now, so far, I haven't really done a whole lot other than just made my switch twice as long as it used to be from a channel length standpoint, right? But I claim this, if I just modify this thing ever so slightly, there's something very nice I can do from the isolation standpoint. So what's nice about actually having two physically separate switches?
You could put a low impedance sort of thing in the middle.
There we go, exactly, right? I can actually hard ground that middle point, right? I can force it to a known voltage. So as an example, what I've drawn here now is, let's say I'm sampling the output and I'm sampling it on the capacitor that, okay, I'll draw it a little bit better. The capacitor is referenced to ground, right? If I want to make sure that none of this makes it through to touch my output, let me just ground the other side of the switch, right? Because if this is grounded and this is a nice low impedance, then even if I have capacitive coupling over there, there should be nearly zero chance for that thing to actually make it all the way through to the other side of the switch. Okay? So by the way, this is known as a T switch. And in applications where, again, you really need very high isolation on the sampling, you may indeed actually have to implement things using this T type of structure. And you should keep in mind, I drew this as ground here. It doesn't actually have to be ground. It's really just whatever your output is sort of quote-unquote referenced to. Okay? Now, this isn't free, unfortunately, because I said earlier, I have to split that switch in half. Right? That means that for sort of the same width, I'm going to have twice as much resistance. Just ballpark, roughly speaking, if not even maybe a little bit more than that. Okay? So, it doesn't come for free, but if you really care about isolation, actually it's a pretty good idea to do this. Any questions? Or Okay. So, kind of the whole reason we started launching into this discussion about resistance is that obviously, if I want to run this thing at a certain speed, I'm going to have to make sure that the resistance is low enough to get kind of the bandwidth that I'm interested in. Okay? So, let's just sort of start out with the simplest kind of model we can think of for that. So, assuming that we know what Vin is and it's just sort of a constant voltage, right? And that this capacitor initially starts at 0 volts, then I basically just have a very simple RC circuit, right? And like we've done a million times already, we can just say that the output voltage, once I've turned on this switch, will basically settle with some exponential time constant, okay? So again, as you can probably imagine, this basically says that if I want to get a certain, essentially, speed of sampling, and I want to do that with a certain resolution, in other words, I want to make sure that my settling error is below a certain relative point, then that basically says, what's the minimum size of the switch that I'm going to have to use? All right, just to basically make this tau such that I get a sufficient number of tau of settling during my sampling time. Now you should just be a little bit careful because you may only have half of the clock period to actually do that settling, because a lot of these things work in 2 phases. But basically that's actually quite straightforward. So this should be sort of, again, very familiar to you in terms of how you deal with this. It's just that now you'd have to actually sort of size this switch to meet this settling constraint. Now, there's just one other sort of quote-unquote minor thing we have to deal with. So in order to sort of write this equation, I had to assume that the capacitance always starts at 0 volts. Is that true or not?
You could make it true.
Ah, okay, well, you jumped one step ahead. So in general, at least with the circuit that I drew here, that's definitely not the case, right? Because the way I drew this here, that capacitor is actually just going to start at whatever value we sampled previously, right? So whatever the input voltage was before, that's where this capacitor is going to start. That's kind of bad news because that means that as an example, let's say I had something that looked like this, and on one cycle I wanted to sample that spot, and on the next I wanted to sample that one. I basically have to completely resettle whatever the previous value was, right? So it's kind of like I'm creating some history in my switch, or in my sampling, I should say. So if I wanted to guarantee a certain settling error, this would effectively like double the rate or double the amount of settling error that I could potentially get. Okay? Now, the good news is, of course, as Dan said, if I really am worried about it, I can just make sure it does indeed start at ground. Right? So I could just make this phi1 bar and make sure that every time I'm taking a new sample, I always start from the same known spot. If you're going at really high speed, this may indeed actually be a good idea, just because you don't want to introduce any sort of history from your previous samples. To kind of put it in the same terms we've been using in our project, this would create ISI, right? So you want to get rid of that ISI, you just add in this grounding switch over here. Now, you may or may not always be able to do that, but for something simple like this, probably a pretty reasonable idea. Okay?
What's ISI again?
Say that again?
What's ISI?
Oh, inter-symbol interference. Remember, so the whole reason you're building the equalizer, right? Okay. So far we've been talking about things as if I knew exactly what that switch resistance is and it was totally fixed. Life is not quite that good. In fact, the resistance really varies with the input voltage. So just to sort of see why that's happening, let's just sort of, again, draw a very simple picture here. So let's say this is my simple sampling circuit. That's my Vin. Of course, this is VDD. Okay? So let's assume I told you that this was a long channel transistor. If you wanted to figure out the effective resistance, I could just write out the equation for basically what's drain current as a function of VGS and VDS, and then sort of take a derivative, and I'd get some kind of effective resistance, right? Okay, so before we dive into doing that, what region of operation should I be using to calculate the drain current of this switch? What do you guys think? The way I'm using it, by the way.
All of them.
All of them. Ah, well, okay. So let's assume I really did it this way. And what I'm really interested in is, while the switch is basically tracking, in other words, I've just got it like this, the gate's at VDD, Vin is at whatever it is, and I just have a capacitive load at the output. What region should that switch be operating in?
Linear, right?
Yeah, it should be in linear. Why?
Because there's not a lot of VDS.
Yeah, in fact, there better not be a lot of VDS, because if there is a lot of VDS, that means I haven't settled the thing properly. Right? In other words, if I really want this output to track the input, there better not be a big drain voltage across the switch. If there is, I'm basically not going fast enough. Right? So in other words, we can say that VDS should roughly be 0 volts. So we should be in the linear or triode region. Which is kind of good news, because doing triode region even for short channel devices is about the same in terms of equations or in terms of estimating the current. Okay? So of course, if we do that, we can just say, okay, the drain current's just mu C aux W over L. Now the only thing we have left is just to figure out what's the VGS, right? Or really the VGS minus VT. Well, VGS minus VT is just VDD minus Vin minus VTH, right? Because my VGS is effectively, doesn't really matter, by the way, if I do it that way or that way, because, again, VDS is supposed to be 0. Okay? So now, of course, I can just complete writing this out, just for sort of the sake of clarity. That would be my sort of full current equation, right? And then if we wanted to know the sort of effective resistance, or in this case, the effective conductance, we just take the derivative of this as a function of VDS at VDS equals 0, which of course just gives us mu C aux W over L VDD minus Vin minus VTH. Okay? Let me rewrite that just so it's clear. There. Okay? So why did I bother kind of going through this whole thing? Well, if we just write out the on resistance, I'm just going to modify this slightly to make it sort of more clear kind of physically what's going on. So the on resistance is just going to be L over W, of course. That's just related to our size. Nothing too surprising over there. 1 over mu C aux VDD minus VTH. Okay? And then I pulled out that VDD minus VTH because I wanted to write this kind of in the following way. Okay? So I wrote this way because notice this piece right here, that's kind of like my nominal resistance from the switch if I had 0 input voltage. Right? So if I gave it like the full VDD, that would kind of like be my nominal resistance. So let's even label that. Let's call that R0. Okay? What this piece right here is telling you, that's the signal-dependent part. Right? So as I change my Vin, this term is basically telling us how much does the resistance of the switch increase. And in particular, because I define this R0 as being the resistance when I have 0 input voltage, my resistance is always going to increase above that. Right? So, why do I care so much about this signal-dependent term? What's that going to kind of do to us?
Distortion.
Yeah, it's going to create distortion. Right? Because basically I now have a nonlinear resistor. So even if I put in nice, perfect sinusoids, at the output, I'm not actually going to get perfect sinusoids anymore. Right? Because this nonlinear thing is going to change the resistance, and it's going to distort the output waveform. Okay? And as you can imagine, the closer Vin gets to VDD, the larger this problem is going to be. Right? So in fact, you can again see there's sort of this annoyance of if you change the swing, that's actually going to have a big impact on the resistance that you have. So in order to really sort of figure out kind of how much you care about this, what you really need to do is take that model and come up with a simple way of predicting how much distortion are you going to get, essentially based on your design parameters. In other words, based on what your nominal resistance was as well as how much basically signal-dependent variation are you expecting to see. Okay? So you can do this in sort of SPICE, but remember, these things that we're going to be looking at, they're like many, many dB down. They're probably 60 to 70 to 80 dB down below the signal that you're interested in. So you really want to do something kind of as a simple model as well by yourself, just so you have something to verify the results you get in SPICE from, okay, or verify against. So all I'm doing here is doing a very simple model. So I'm just going to assume that if I want to sort of characterize this, I'm just going to take that switch, I'm going to put into it some sinusoid, still the gate at VDD, and then just put the capacitor right there. And so all I can do is sort of just in MATLAB or something like that, run a very simple simulation where I just say that, okay, the output is going to be the input times this sort of exponential settling term. Okay? With that exponential settling term, this tau here, that's just coming from my nominal resistance at, for example, Vin of 0 volts. And then this term right here is just capturing the signal-dependent resistance. Okay? So if this switch was perfect and I put in this perfect sinusoid and I measured the output, and then I just do an FFT of that output, you'd expect to see something that just basically had a single tone at the frequency that I put in, right? But because that switch has distortion in it, what's going to happen is I'm going to get basically harmonics coming out of there, okay? So what I'm going to be interested in is essentially how big are those harmonics relative to my main fundamental tone. Okay, that's kind of like a measure of the distortion that I'm introducing. So here, let's just sort of take a look at the results in two different cases. So first, what I've done here is I've made the frequency of the sinusoid basically high enough that the period of the sinusoid is 10 tau. Okay, where again, tau is just coming from the nominal resistance of the switch. So what you can see here is that basically that first harmonic term, that's basically or I should say it's really this looks like it's the third harmonic down. That one's at about minus 50 dB lower than my fundamental tone. Okay? So that's pretty good, but that's only about, I don't know, 8 bits or so. Right? So that basically says that if I want to get more than 8 bits of resolution in my sampling, I can't actually run at this speed, right? Because notice there isn't a whole lot I can really change here, right? Because I have a certain switch that I've sized to meet, let's say, a certain bandwidth. And if I'm trying to run at this particular speed, sorry, that's the distortion that you get, right? In fact, really from a design standpoint, the only thing you can kind of do to try and improve this is over-design the switch. As an example, if I made the switch somehow twice as fast nominally, now you can see the distortion is down at like something like minus 70 dB. So I gained myself an extra, I don't know, 3 or so bits, right? So by the way, just intuitively, just to make sure it's clear, why is it that making the switch even faster helps to really reduce this distortion? Why is it that I really care about sort of how fast the switch is relative to this sinusoid?
Your VDS stays closer to 0.
Okay, the VDS gets closer to 0. You're right, but why is that sort of important?
You just need to oversample if you want to reduce aliasing, right?
That's not quite the issue, because what I'm really talking about here is just, when I say T over tau is 20, all I really mean is that the nominal resistance that I chose for this thing, in this case versus that case, is twice as small. So I'm not actually changing the sampling rate, I'm just changing the size of the switch. So as Brian said, I'm going to be making the VDS go closer to 0. Why is that sort of good from a distortion standpoint? And by the way, it has nothing to do with the device itself in terms of, you know, the weirdness of changing modes of operation or anything like that.
This is the equation that you wrote as you increase the...
Okay,
higher
I mean,
range
that's
VDS,
true,
more distortion.
but I want something really intuitive, right? So maybe just to be clear, the situation we're basically in just looks something like this. I have a sinusoid, some varying resistance, and a capacitor, right? Okay, so if I waited forever, or rather I should say, if the sinusoid was super duper slow, what has to show up over there?
Same.
Yeah, it has to be the same, right? No matter how grossly nonlinear that resistance is, unless it's like completely turns off or something like that, eventually this output over here had better match with the input, right? So the reason that making the switch faster helps is that even though it's nonlinear and it creates distortion, if you wait long enough for everything to settle, then it better be the case that the output matches the input, right? So by making that switch nominally faster, all you're trying to do is really make sure that the output voltage tracks perfectly with the input voltage, even as this resistance is varying, right? In other words, even in kind of the worst case resistance, you're trying to set that tau to be fast enough to track the input sinusoid, okay? So this is kind of actually bad news again, because this says that if you want to get a certain resolution, you basically have to upsize your switches sufficiently to get kind of a certain bandwidth, or to get much, much higher than the bandwidth you might have nominally expected just based on sort of that linear settling calculation we had done earlier. Okay? So again, that's kind of bad news because pretty quickly you may even find that no matter how large you make the switch, you can't actually sort of get the settling bandwidth or the settling resolution and speed that you wanted. So by the way, anything else that you can do to maybe try and make this a little bit better? Other than, of course, really modifying the circuit in a huge way? Anything else you can try and change? If this is really what's totally limiting you, anything else you could actually sort of try and change? Other than just brute force sizing up the switch. What's causing the variation in the resistance?
This is changing.
Yeah, the VGS is changing, right? Okay, so how can I make the change in the VGS smaller?
Increase VDD.
Ah, okay, yeah. Yeah, that's actually exactly it. Increase VDD, or equivalently, somehow make VN smaller relative to VDD, right? That's actually exactly what I wanted. Now, why do you not want to do that?
Power.
Okay, so if I increase VDD, I'm paying more power. If I decrease VN, what's going to happen?
SNR.
Yeah, basically I'm going to have more noise, which effectively is going to mean I'm going to have to pay more power because I'm going to have to increase the size of the cap. Right? So for both of them, it's kind of bad news because it just costs you more power to do sort of the same thing you used to want to do. Okay? Now, the good news is there's actually even one more trick you can play here, which we actually sort of hinted at already. So both of those directions we're really talking about how do I try and reduce the change in VGS? Well, rather than fight with the signal swing or increasing VDD or anything like that, instead, why don't I just force VGS to be constant? Right? Why don't I just make sure that no matter what the input voltage is, I always get the same VGS? Because if I do that, then now, at least to first order, my resistance should be constant, and I shouldn't get any distortion out of the switch. I should get basically just a constant resistance, which then would give me my standard linear settling error. Okay, so conceptually the way this would work is I have some switch and I ground its gate. And then when I want to turn the thing on, rather than just tying this to VDD, I always tie the battery from the source to the gate. In other words, I try and maintain a constant voltage from the source up to the gate. Okay? So conceptually, this actually works beautifully well. Now, why is this kind of a pain in the butt? Or what's sort of annoying about this?
It's hard to
The
integrate.
batteries lying around.
Yeah, I gotta have batteries lying around that I can just move and sort of place in random spots, right? Okay, turns out that's actually not so bad. What's a really good approximation of a battery?
Giant capacitor.
Yeah, a capacitor, right? So actually, the way we're really going to do this is basically fake a battery by building a capacitor. Okay, so let's actually take a look how you might do that. So first of all, when I'm doing this constant VGS sampling, what I probably want to do is make it so that I always put VDD of VGS across my switch. Right? Because that's kind of like the most in order to get like the lowest resistance per unit width, I probably want that maximum gate overdrive, right? So the value of that battery or the value of the voltage source should probably be VDD. Okay, so like we said, we're going to approximate that with a capacitor. So the way I'm going to do that is, in some initial phase, I'm going to charge a capacitor up to VDD. Okay? Well, then once I've done that, in the second phase, all I'm going to try and do is take that capacitor, which again is approximating a battery, and tie it up onto the gate and the source of the switch, right? So if I've done things right, then across here, I should always be maintaining VDD, right? So just to be clear, the way this would sort of work is my VIN would be tied right there, okay? And this is where my sampling capacitor would be, and of course, in the other phase, I would just turn off that switch, okay? So indeed, this actually basically does what we want. Now, I have to be a little bit careful because this is obviously a capacitor and not a battery, right? But if as long as I make that capacitor big enough relative to the capacitance of the switch, this indeed behaves essentially the way we want it to. Okay, so again, just to sort of be totally clear, the way something like this would work is, if this was my V in, and I wanted to look at my gate voltage, let's call that VG, then while the clock is low, obviously my VG will be at ground. Then when the clock goes high, I'll have whatever the input signal is, plus VDD on that gate, right? Then once I'm done sampling, okay, again, this goes to ground. I sample again, it goes up to VDD, and then tracks with the input. Then ground, back up again, tracks with the input, and so on and so forth. Okay? So again, really all this is trying to do is just make it so that when I am indeed sampling, I basically maintain a constant VGS across that switch. Of course, the only way to do that is to have the source track with the input, and so that's why I built this quote-unquote floating battery out of this capacitor here. Okay? So now, just sort of based on the waveforms that I drew here, anything you think you're going to have to be a little bit careful about when you actually build this thing?
Common mode of the output?
Say it again?
The common mode of the output, or like, not the common mode, but like the DC level of the output?
I think, so by the way, this is VG that I drew here.
Oh.
Right, so that's, VG is, I didn't, the output, if I've done things right, should just be, I'll do that in blue, V out should be tracking with the input. Right? Because that was kind of the whole point of building this thing. What do I need to be a little bit careful about?
Glitching?
Say that again?
Glitching?
Glitching. Okay, yeah, that's probably true. There's maybe some weird glitches and things like that. There's actually one more thing. Why do you usually say that you used a certain VDD in the process to begin with?
We don't blow up your gates.
Yeah, so you don't blow anything up, right? Because let's say it was your 90 nanometer process and it was 1.2 volt supply. If you put 2 volts onto those transistors, they pretty much literally pop. Okay? Now, the good news is, for this sampling switch right here, because I'm making the VGS constant, I'm probably never going to actually overstress that one. Right? Because I've just made it so that the VGS here is always VDD. So that's okay. How about these other switches, though? Am I safe with those, or do I need to be careful?
Be careful.
Yeah, I got to be careful, right? Because this voltage over here, like you've seen, if this was up at VDD, that VG definitely above VDD, right? So I got to be really careful with how I build these switches. A, to make sure they don't blow up, and B, to make sure they actually behave the way I want them to. Okay? So as an example, let's see what's one sort of bad thing that might happen if I'm not careful. So let's say I built that switch right there out of a PMOS transistor. Okay? And let's say that when that switch was on, or actually even when the switch was off, let's say that this gate here swings from 0 to VDD. Okay? So let's think about like this phase right here, when you're trying to put basically this capacitor across the gate to the source of the switch right there. So in that phase, do you want this switch to be on or off? When you want the capacitor sort of in parallel with the sampling switch.
Off, right?
Yeah, you want it to be off, right? Okay, so let's say that Vin happened to be VDD. What should VG be when Vin is at VDD?
2 VDD.
Yeah, it better be 2 VDD. Now, this switch, of course, is on, so how about that PMOS transistor right there?
It's going to be forward biased towards the body. Right?
Yeah, not only do I actually have a diode that's turned on, which of course is just this one, but in fact, the transistor itself is actually going to be on also, right? Because remember, PMOS, whatever the higher voltage is, that's the source. Okay, so I've got 2 VDD over here, I've got VDD at the gate. Guess what? That PMOS is nicely on. In other words, ain't going to work, right? And not only that, you turned on a diode and you may have blown something up and you're generally unhappy. Okay? So why did I mention all this? Because turns out, even though conceptually what I drew there is actually pretty straightforward to do, there's a lot of details that you have to be very careful of to actually build this thing the right way. Okay? So this was actually originally done by a guy named Andy Abo, who was a student here at Berkeley. It was originally published in May 1999. But this is kind of a slightly simplified view of the circuit that he came up with. So I'm just going to walk through a couple of the pieces here, but really the most important point in all of this is this was the switch. This was the capacitor we were trying to put in parallel with the thing. And all this other junk around it is just to make sure that all of the rest of the switches don't blow up. Okay, or don't turn on when you don't want them to. Okay? So let's just kind of walk through how this thing works. So first of all, what you can see here is, you remember I needed those 2 switches to basically charge the capacitor up to VDD? Okay, so the switch that connects me to ground, that's nothing magic, that's just an NMOS transistor. Okay? But the switch that connects me to VDD on this top plate of the capacitor, I'm actually also going to build with an NMOS transistor. Okay? Because as you saw a second ago, if I used a PMOS right there and I wasn't really tricky with how I drove the gate, it would actually turn on or basically just not work at all because I'd be forward biasing some diode. Okay? So instead what I'm actually doing here is I'm using an NMOS transistor. I'm just going to be a little bit clever because what I'm going to do is I'm going to make it so that this gate voltage right here swings from VDD up to 2 VDD. Okay? Well, the way I do that is with this so-called clock multiplier, which is kind of the thing that I've boxed in red right here. It's also sometimes called a charge pump. Okay? Which notice, by the way, these two are also NMOS transistors. Okay? By the way, how many of you guys have seen this kind of either clock multiplier or charge pump before? Okay, a few of you. So just in case you haven't seen it before, the way this thing works is something like the following. So assume for a second that this starts at VDD. Just believe me that somehow magically it got there initially. Okay? When this clock signal right here rises from 0 up to VDD, that'll just capacitively couple and kick this voltage up, right? Roughly speaking, it should kick it up to about 2 VDD. Well, once I kick that voltage up to 2 VDD, notice this NMOS transistor right here, it should turn on, right? Once this thing is on, of course, this right here is just VDD. So that means that this point right there should also go to VDD. Right? I'm just clamping it to VDD. Now, when the clock goes back low, on this side, I'll get kicked back down to VDD. But on this side, I'll get kicked up to 2 VDD. Right? And notice now that I have 2 VDD over here, I'll turn on this switch, and this will get forced back to VDD. Okay? So essentially, all I'm doing with this whole circuit right here is just trying to generate this clock waveform that goes between VDD and 2 VDD to turn on and off this NMOS switch right there. Okay? Does this make sense to everybody? Or? Okay, by the way, these are very, very sort of common There's a lot of places in sort of even in digital stuff where occasionally you just want stuff outside of the supply rail. A very common way of actually doing it. Okay, so that's what this NMOS switch right here is doing. All of kind of this stuff right here, all of that just has to do with basically making sure you can actually connect this capacitor across the VGS of the input of the sampling switch without blowing anything up. Okay? So in particular, there's one sort of simple thing that was done here, which notice there's this M7 in series with that M10. This M10, that's just the one that turns off the sampling switch when you're not using it. What is this M7 kind of doing? What type of transistor is that? I mean, I know it's an NMOS device, but like, what would you call that? Okay, it's a resistor, or actually you were the one who suggested this earlier. Ah, there we go, cascode. All right? So why is this cascode actually sort of saving me here? Why is it making sure that this NMOS device doesn't blow up? What's good about this cascode? There we go. Yeah, that's exactly it. Right? So basically, in the worst case, this point right there is going to go up to 2 VDD. Right? Well, if that goes up to 2 VDD, the source of the cascode is going to be over there. Right? Well, the gate of that cascode is at VDD, so no way that that thing is going above VDD. Right? So now if I look at the cascode device, it's got VDD across one side. It's got 0 volts across the other side. My bottom switch has only got VDD across it. And so nothing is actually going to be overstressed. Right? So I point this out because, again, as I mentioned, there's going to be a lot of times where you're going to want to use voltages that are larger than kind of what your process can nominally handle. Turns out this simple trick right here lets you get away with basically up to about twice of the nominal process voltage without too much sort of muss and fuss, so to speak. Okay? You can, of course, do the same thing with the PMOS devices as well. Okay? So I'd encourage you to sort of take a look at this 4 or 5 transistors that are added here once too. Just make sure you understand sort of what's going on there. But really, all they're trying to implement conceptually is exactly this thing. They're just doing it in a way that makes sure that nothing blows up and things don't turn on and things like that when you didn't want them to. Okay? Does this kind of make sense to everybody? Or? Okay, so now we at least know how to get sort of relatively constant resistance out of our switches. By the way, this isn't actually completely perfect because even after I've done all this, unfortunately you still have that body connection there. So you're still going to have variation in the resistance because of the body effect. But once you've done this, you can get really, really high resolution sampling up to some pretty high speeds. So that's usually not too big of an issue, but keep that in mind because, not perfect either. So we have a good idea of sort of how to get high resolution, high speed sampling. But unfortunately, life is not quite over in terms of the badnesses that these switches can actually introduce. So in particular, let's just sort of take a look and think about what really would happen if we have our transistor there with some control signal, some input signal, and I sample it onto a capacitor. Okay? So right at the time when my control signal goes low, let me just sort of draw this in a different, I'll do it in a different color. So let's say I look at my V in, my V out, and I'll do V out in a different color just so that it's more clear. Okay? So let's say my V in was constant. I was just trying to sample that constant voltage. Okay? Well, once I turn off the switch, unfortunately that switch, it had some sort of channel charge inside of there. Right? Well, when I turn that thing off, that charge has to go somewhere. It can't just disappear. So unfortunately, some of that charge is actually going to flow into the output. If you think about it, what that means is that once you've turned off that switch, your output is also going to have this like droop on it. Because it's an NMOS transistor, I had electrons inside of the channel. Those electrons flow out onto the capacitor. They induce a negative change in the voltage. Okay? Now, by the way, I've sort of talked about this as being just the charge that was inside of the channel, of course. You've also always got some CGS or CGD, so there's just going to be some direct feed-through that also knocks your output voltage down. So this error, unfortunately, is basically always going to be there. And because of that, people even came up with sort of a special name for it. So if you look at this output right here, the difference between your ideal output and where you actually end up is known as the pedestal error. Okay, don't ask me exactly why. It just has something to do with, it's like you're on a pedestal, the input's above the output, something like that. Okay, but basically that error is the pedestal error. So essentially this sort of causes us two problems. One is, clearly there's an offset, right? If I wanted to sample, let's say 1 volt, and my pedestal error was 50 millivolts, I've got an offset by 50 millivolts. The other, which is going to turn out to actually be a little bit more nasty, is again going to be distortion. Because unfortunately, the amount of charge that I actually store here is again going to be a function of my input voltage. Okay? So because of that, this error is going to change with the input voltage. And if it changes in a nonlinear way, it's going to create distortion. Okay? So just in case you sort of don't believe me as to why I'd even bother thinking about this, because maybe it's really small, well, unfortunately, it's not all that small. It can actually be quite big. Because remember, you have to size this switch up to get a certain sampling speed, right, to get a certain, basically, settling error. That basically means that the size of this switch is going to be directly set by how much capacitance you have to drive in the first place. Well, the larger I make this switch, the more charge you're going to be storing in the channel, right? That therefore means that if I look at the ratio between how much charge I stored in the channel and how much does that charge affect the output voltage, all of this here, basically you can't really do much about from a design standpoint because you just don't have any degrees of freedom left, right? Because once I've sized this switch to get a certain speed, that size was set by this capacitance. So this ratio here basically ends up being a fixed number. Okay? And if you just walk through what those numbers are, you can very easily get, 40, 50, even 100 millivolts types of pedestal errors. Okay? And I think this was done, I think I did this with like a 0.35 micron process, but the numbers aren't actually all that different for your technology. Okay? And you guys are working so hard to like get rid of your 20 millivolt offsets in your comparators. If you had this and you didn't do anything about it, now you've got 50 to 100 millivolts, right? Obviously bad news. So something you're definitely going to want to try and fix, right? So, what can we do to try and actually fix this? Any ideas? Anything we can do to try and get rid of this problem? There's actually a few different ways, by the way. Yeah, there we go. So that's actually the first solution. Why don't we try and take some charge away? Because we knew that the problem was all about when we turned this thing off, some charge jumped onto our capacitor. Why don't we just try and suck that charge off, right? So actually that was one of the first sort of ideas that people came up with. So essentially the way you'd suck some charge off is every time you turn off this switch, turn on some other switch, and hope that you've sized that other switch so that however much charge jumped off of this thing gets sucked up by your dummy switch. Okay? That's actually exactly the idea. So now let's see sort of if we can figure out how this would really work and how well we think it should work. So in particular for this, so kind of the standard way you try and make this happen is if this switch has a certain width W, you make this dummy switch have a width of W over 2. So why did I do that? Why did I make that dummy switch have a width of W over 2? What am I sort of relying on there? Yeah, basically, so what I'm saying is that when I turn off that main switch, if half of the charge goes to the left and half of the charge goes to the right, then I should size this switch up so that it grabs only that half of the charge, right? Because if I made this too big, I would actually be grabbing more charge than was being sent back by this first switch. Okay? Now, unfortunately, this is kind of where the problem really comes in. When I just sort of decided that this was W over 2, I had to guess that really half of the charge was going to go that way, and half of the charge was going to go that way. Well, it turns out that may not actually be true. In particular, what do you think, under what condition can I try and force that to be true? What do you think has to be sort of the same in order to make sure that half of the charge goes this way and half of the charge goes the other way?
VDS has to be 0.
Okay, VDS has to be 0. What else? I mean, by the way, because this is a dynamic thing, because I'm turning it off with some edge rate, so what else sort of is going to impact this?
The impedances seem...
There we go, the impedances, right? Because let's say I had 0 impedance right there and an open circuit right there. Well, clearly, all the charge is going to flow into the 0 impedance, right? So in fact, in order to make this work, what the people who originally came up with actually tried to do was intentionally muck around with a circuit to try and force the impedance to be the same on the two sides. Okay, so you can see they added this CD right here. And the whole reason for adding that CD was to try and make it so that the impedance on the left side looks similar to the impedance on the right side where we have this sampling capacitor. In fact, not only that, right, this is my input voltage over here. So if that had a too low of an impedance, then all of the charge or a lot of the charge would get sucked out over there, and you wouldn't know how big to make this dummy switch. So not only that, they actually even added an extra series resistance here. That's clearly bad news, right? Because now I've got just extra filtering on my signal path. Clearly not what you really wanted to do, right? So the good news is if you're not super concerned about getting this exactly right, this does help, right? So you can kind of see from the table here, if you hadn't done anything at all, you would have gotten 160 millivolts of basically error. If you just added this little dummy without doing anything else, you would have gotten about 45 millivolts of pedestal error. And then if you do all of this extra stuff around it, you can get it down to maybe 6 millivolts. But unfortunately, this extra stuff around it is kind of painful. Okay? So it does help, but not quite perfect. So if you really wanted to kind of get things exactly right, what you'd actually need to do is kind of do a very careful analysis of how much charge is going to split in which direction, and where is that charge going to sort of end up in. The bad news is that sort of analysis is a bit of a pain in the butt. Okay? The even worse news is that SPICE can't actually do it for you. Okay? So if you really want to sort of answer that question, you need to go in and actually do the analysis yourself. Now, fortunately, somebody obviously has done this once, so you can kind of get an idea of how they do it. The basic principle looks something like this. So essentially what you do is, if you think about your transistor, what you're really trying to do is figure out, okay, right at the instant or during the time that this thing is being turned off, how is the charge going to flow inside of that transistor? Well, the way to kind of model that is just to realize that, okay, charge in the channel is kind of just like saying that there's some, let's say, equivalent resistance at each point in space, right? Where that resistance, of course, depends on how much charge is at that particular spot, okay? So if you wanted to figure out basically how much charge is going to flow to the left and to the right, at kind of like each instant in time, you could calculate what is this effective resistance at each point along the channel, figure out for that given time step how much charge is going to flow this way versus how much charge is going to flow that way, which of course is just set by the current in the device, and then just repeat that process over a small enough time step while the gate voltage is actually ramping down. Okay? So as you can imagine, the actual result you get in terms of where the charge goes strongly depends on sort of the distribution of charge in the channel, the relative impedances on the two sides, and actually how fast you change that gate voltage. Because as you change that gate voltage, that changes these resistors inside of the channel. Okay? So it's a bit complicated, but if you really, really need some sort of high accuracy kind of sampling, this is really the type of analysis that you have to do. Okay? Now, as I mentioned before, the bad news is that SPICE can't really help you here. Because if you sort of think about everything we just described, this is like a distributed model of the transistor. Right, we're talking about things that are happening basically faster than sort of when the transistor can turn on and off. Right? It's kind of like all this stuff happening inside of the transistor at these really, really fine time scales. SPICE models, or particularly BSIM3, doesn't know jack squat about this. Okay? It just has a pile of equations that it uses to kind of estimate the overall current flow. But it really doesn't know anything about sort of all this charge distribution and stuff like that. Now, you can probably build some more sophisticated models that would, but basically nobody does it because you can imagine if you use those models to like simulate every single transistor in your design, it would take forever and a day, right? So in SPICE, what SPICE really does is it just has sort of a lumped model for this whole thing. But because you know that this is an issue you have to pay attention to, what SPICE will do is basically say, okay, well, I'm just going to rely on the designer to tell me which way he thinks all the charge is going to go, or how much of the charge is going to go to one side or the other. So in SPICE, if you look inside of the model, you'll see there's this parameter called x part. Okay? Depending upon what you've set that x part to, SPICE will just automatically send the charge to one side or the other with some basically ratio that depends upon that x part setting. So as an example, if you set it to 0, SPICE will assume that 60% of the charge flows to the source and 40% flows to the drain. Okay? If you set it equal to a half, it'll split the charge equally. And if you set it equal to 1, 100% of it will flow to the drain. Okay? Now again, this has no physics behind it. This is just you as the designer assuming you know which direction things are going to go. Okay? So if you wanted to sort of do like a worst case analysis to try and check if your circuit's going to work even under that really bad condition, what you'd actually have to go and do is set x part to 1, then tie your circuit up to make sure that the drain side is the one that you're really sensitive to. Okay? So that all of the charge would flow onto that capacitor that you care about. By the way, when I talk about source and drain here, I just mean which terminals you instantiated as source and drain in like your SPICE deck. Right, so whichever one you called first, that would be source, then it would be drain for the second one. Or sorry, it's actually, I guess it's a... So I just mean that when you say like M1, drain, gate, source, body. So it always would treat that as the drain, always this terminal as the source. Okay? Yeah? Spectre, I believe, does the same thing, because it really just has to do with, essentially, you have a lumped model rather than a distributed model. So I believe it'll do the same thing, and in fact, Spectre should read BSIM3 or BSIM4 decks that should have this X part parameter in it as well. Other kind of questions on this, or? Okay, so from sort of 30,000 feet, what you should get from this is that this is, again, a big pain in the ass. So obviously, we're going to want to try and do something to fix this. So what do you guys think? Is there something we can do to actually fix this, or are we just sort of hosed? Other than the dummy switch, of course, which we already talked about. So we talked about sucking the charge out. We said it sort of works, but it was a little bit hard to actually get things right. Any other thoughts?
If you do sort of know what the charge injection is going to be on the cap, can't you just pre-charge the cap?
Okay. That's not such a bad idea. So let me maybe sort of jog people down that direction. So let's say I just have my sampling switch. I've got some V in over there. I've got some sampling signal. And I've got my cap over there. right? So what we're kind of saying is happening with this charge injection is that the output is, of course, going to be my input, but it's also going to have some offset in it, just because of basically when the switch turns off, there's some fixed amount of charge that's going to jump into the output. Plus, we're going to have some residual amount of error that's dependent upon the input voltage. Okay? Let's ignore that residual error that depends on the input voltage for now. If I just told you that I always knew how much charge was jumping into the capacitor. So what you were saying was, okay, well, maybe what I could do is kind of like always suck off exactly that same amount of charge. So you might be able to do that. That's a little bit sort of tricky. But there's actually sort of another way that does the moral equivalent. So what's the moral equivalent of sort of sucking off that same amount of charge, or doing something that will knock this offset off?
Yes.
Change the input to get rid of that?
Okay, almost. I mean, yes, you're sort of going down the right path.
Try to make it a common mode error.
There we go. Right? So if this offset really doesn't depend on the input, then at least in principle, I could do something like the following. I could take that same sampling switch, right? And how about I just sample some quote-unquote reference voltage, right? So now if I look at this output, I'm going to have, of course, V in plus that offset plus some function of V in. If I look at this one over here, I'm going to have that Vref, which again I'm going to put in quotes, plus some offset, plus some function of Vref, right? Well, so how would I get rid of that offset? What should I take as my output voltage? Yeah, the difference, right? So in other words, if I just look at the difference between that one and that one, then what I'll end up with is something like V in. And by the way, I'm just going to replace this Vref with V in minus now. And that V in with V in plus. Right? In other words, I'm just going to make this sample differentially. If I look at the differential output, all I should get is the differential input, and then plus just whatever this difference is, right? So it's going to be some other function of the input differential voltage, okay? Again, simply by sort of rearranging how I kind of use this thing, at least I can make the errors that are constant, I can kind of make that common mode, right? It'll shift both of these outputs, but it won't directly impact the thing I care about. Okay? So that's good news. So now the only thing that I have left that I still need to probably fix, or potentially fix, is this darn thing. Right? Because I still have this distortion that actually depends on the input voltage. Okay, and by the way, that, again, if I'm shooting for like 10, 12, 13 bits, particularly at high speed, this could actually be a big impact on things. So what's the only thing I've got left to sort of help me in terms of getting rid of this? What do I have to make true? How can I make this term sort of go to 0, or at least be constant? By the way, it's a little bit of a trick question. If I wanted this to be 0, and by the way, I've only got one thing I can kind of control here. So if I wanted this to be 0, what do I have to do?
Make V in diff 0.
Yeah, I have to make V in diff 0. Exactly. Or to say it another way, I have to somehow make it constant. Okay, now, so that sounds really dumb, because if I made V in diff 0, then I don't know what I'm actually sampling anymore, because I have to make it 0. But turns out there's actually a very clever way you can do this. Okay? So the way you do this is what's called bottom plate sampling. So what I'm going to do is now, rather than just having one sampling switch, I'm actually going to split my switch into two different pieces. Okay? So the way this is going to work is as following. This is kind of like my original sampling switch, and this is kind of like my sampling capacitor. But now, rather than looking at the output from here, I'm going to take the output from the bottom plate of that capacitor. And not only that, I'm going to add a switch in series with that capacitor and ground. Okay? So why did I do that? Well, if you think about this switch, its quote-unquote Vin is always 0. Okay? Because I should always just have ground on the two sides when the thing is on. Right? So when I turn this switch off, the amount of charge I inject into the output should always be the same. Okay? Because it's always set by this ground over here. Right? So now, if I turn this switch off first, okay, so I inject some amount of charge over there. Then I turn off this switch. Okay? But once I turn off this switch, since this guy over here is already open circuit, I should see a high impedance looking in that direction. Right? I've got no path for that charge to actually flow through. So that means that all of the charge from this switch should actually flow back into the input. So all of the badness that I would have gotten shouldn't actually show up across my capacitor. Right? So indeed, I can somehow sort of have this output over here, and it will indeed have charge injection on it, but at least it's constant. Now, of course, the only bad news here is that still, if I look at that relative to ground, then kind of by definition, I still don't have any output signal, right? Because I've just sort of sampled ground there. But where do I have the input signal stored? Where's the input signal sort of showing up?
I guess just across the cap.
Yeah, exactly. I'm just storing the input signal across that capacitor right there, right? So in order to actually make this useful, rather than measuring the voltage across here, all I actually have to do is measure the voltage across that capacitor. Or rather, basically use the charge that's stored in that capacitor to actually affect my output. Okay? So let's see how we can do that, and actually in a way that should be very, very familiar to you guys. So in fact, I claim that that switched capacitor amplifier that I showed you guys a long, long time ago, you could actually modify it ever so slightly to do exactly this bottom plate sampling trick. Okay? So let's take a look at that. So if you guys remember when we sort of looked at these switched cap amplifiers, we usually built it to look something sort of like this. And I've added in just a couple of extra switches, but bear with me and you'll see why I did that in a second. Okay? So what I'm going to do here is the following. So let's just call this phi 1b. Let's call that phi 1a. Let's call this phi 2 and this phi 2. Okay? So by A and B, I'll just draw that over here. So phi 1a is going to turn off before phi 1b does. Okay? Because what I'm trying to do there is exactly that bottom plate sampling that we just looked at a second ago. So in other words, I turn this switch off first, and then I turn this switch off. So in other words, in the first phase, this whole circuit just looks something like that's my V-in, that's the capacitor. I have my OTA sitting over there, just in the standard negative feedback, right? And I might even ground this just to reset it. Okay? So that's phi 1. Then I turn this switch off. I get some charge injection onto the capacitor, but again, it's a fixed amount of charge because this is just ground. I turn off this switch, and then I turn on this switch and this switch. So I just get the amplifier into that configuration, which again should hopefully be very familiar to everybody. Right? So notice the whole reason I did all this is, again, because now I can actually ensure that any errors that I got from my switch, in terms of charge injection and glitching and all that other stuff, basically is going to be constant. And you can imagine if I do the same thing on the differential side, I'm basically, not guaranteed, but I've got a really, really good shot at making all of these errors not only common mode, but constant. Okay? Does this kind of make sense to everybody? Or?
So we're kind of kicking our charge injection into our input signal.
This is true. So that does mean that whatever whatever is driving that input better have sufficiently low output impedance, right? Now, the good news is that if you're driving it from some other OTA and feedback, that means it should indeed have relatively low output impedance. But you're absolutely right. If I did this with something that had a very sensitive input, you better be careful, because I'm going to be kicking that charge back onto that input, and if that input can't handle it, then when you come back around, you'll again be picking it up. That's a great point. Other questions? Yeah.
I mean, if this is done for very high speed, can you afford to lose that 20, 30 picoseconds for the two different clocks?
Good question. So, indeed, if you look at things that are doing at very, very high speed, a lot of these techniques are trickier to use. Because not only is it hard to sort of guarantee that you really get that non-overlapped clock the way you want it to, but also actually, basically the sampling rates or the sort of the distortion you can tolerate is pretty small. Because to get up to really high speeds, that means that T over tau is not very large, right? So you're right that actually if you look at like really, really high speed stuff, so multiple gigahertz, this isn't quite as common. The good news is you can actually push this up to much higher speeds than people used to be able to, just because the switches are indeed very fast. But you're absolutely right. If you push this out to the real limit, it gets pretty tough to use. But by the way, it's always pretty tough to build like 10 or 12-bit converters running at multiple gigahertz, because just if you sort of think about the relative precision you need and the time scales, you get to these really ridiculously small numbers. So that's a hard problem in any case. So this is certainly one of those hard problems that are part of that, but it's not the only one, I guess I should say.
That's an ISOCC paper.
Yeah, so if you can build like, a 10-bit, let's say 3 gigahertz ADC and it doesn't burn multiple watts, that's definitely an ISSCC paper. Other questions on this? Or? Okay, so just one last thing to sort of quickly wrap up. This is just really showing you sort of the same bottom plate sampling that we've already been talking about. This is just kind of, again, this is also giving you the reference of one of the first people that sort of made use of this. There's just one other thing we have to be really careful about, particularly in the differential implementation, which is when you're doing all this, you're really relying on making basically this offset error be common mode, right? Because that's really how you're sort of knocking this thing off, is you're just trying to ensure that whatever offset I pick up here is the same offset I pick up there. But you can imagine if anything is slightly imbalanced, unfortunately, that's not going to be true. You're actually going to get, again, some basically residual offset. And worse than that, some residual distortion because of the fact that offset depends on the signal. Okay? So whenever you do these things, you have to be really, really paranoid to make things absolutely symmetric. So in particular, when you add, like, for example, if you look at this bridge switch right here, which is trying to reset the differential output to 0, you better make sure that when you turn that bridge switch off, it really is going to be perfectly symmetric in terms of kicking back charge onto the two sides. Okay? So if you think sort of a little bit carefully about that, what that means is that the way you're going to want to build this looks something like the following. So if let's say this is VO plus and VO minus, if you take that switch and let's say you tie it up like this, let's say that's the source and that's the drain. Remember, all the implants and everything are slightly directional, right? So if there's any sort of asymmetry inside of that switch, some charge may split unequally, okay? So what we're actually going to do, just to, again, be sort of absolutely paranoid, is take another copy of that switch, where, again, this is the source and this is the drain. But now, I'm going to swizzle the connections. Okay, so if the source used to be connected to VO plus, now I'm going to tie the source to VO minus. Similarly, if the drain used to be connected to VO minus, now I'm going to connect it to VO plus. Okay? And again, I'm doing this just to be absolutely paranoid to make sure that my charge injection is totally balanced between the two sides. And by the way, in case you didn't remember, this was probably a good idea anyways, because if you wanted to match anything, you probably wanted to basically have the transistor so that current was flowing in both directions. In other words, so that you always used two fingers and you had current flowing in both ways. Okay? So same idea here, just if you want to be absolutely paranoid to make sure that you don't get any extra errors, you better make sure the thing is really completely symmetric. And only way to do that is indeed to do something like what I've drawn here. Does this kind of make sense to everybody? Or? Okay, any last kind of question on switches and sampling? Okay, so next time we'll sort of finish things up with talking about kind of some timing circuits and how you'd actually figure out where to place your sampling clocks. And we'll also definitely sort of cover any last questions you have on the project. So see you guys on Thursday.